Hey, what's up guys? It's Nicola from Calcunic, and today we're going to be talking about geometric series. Let's get right into it.
Alright, first we're going to talk about finite geometric series, and in the second part of the video we'll talk about infinite geometric series. So, a finite geometric series, call it Sn, is of the form a plus a times r plus a times r squared all the way to a times r to the n. Notice that what makes this a geometric series is that every other term is just r times the previous. We could write this expression in the form of summation notation to make it look a bit more clean. However, we wish to find an algebraic expression for this summation in hopes to be able to find the answer to these sums much faster. The first step is going to be to multiply both sides by r. On the left-hand side, we'll have r times Sn, and this is equal to ar plus ar squared plus ar cubed plus all the way to a times r to the n plus 1. Now what we're going to do is subtract both of these equations. And we'll notice that on the right hand side, a lot of these terms actually cancel out. We have ar cancels out, ar squared cancel out, ar cubed will cancel out, all of this in between will cancel out, including the ar to the n, and all that's left is going to be the ar n plus 1 term and the a term. But first, let's start with the left-hand side. We have Sn minus r times Sn is equal to a minus a times r to the n plus 1. Doing some factoring, we could get on the left-hand side Sn times 1 minus r is equal to a times 1 minus r to the n plus 1. Simply rearranging for Sn, we get that Sn is equal to a times 1 minus r to the n plus 1 all over 1 minus r. Let's see if we could use this expression to solve some examples. We're asked to find the sum of 1 plus 2 plus 4 all the way to plus 2 to the power of n, where n is just any positive integer. The first step, of course, is to recognize that this is in fact a geometric series. It's pretty clear to see that this is in fact a geometric series, as each term is twice its previous. Now we wish to determine a and r so we could have that into our equation to find the sum much faster. Well, the first element is 1, so that means that a is equal to 1, and as mentioned before, each term is twice its previous, so therefore r is equal to 2. Let's call this sum s. From before, we have that the sum is equal to a times 1 minus r to the n plus 1 all over 1 minus r. Inputting the values we just found, we get that this is equal to 1 times 1 minus 2 to the n plus 1 all over 1 minus 2. Now, if we do a bit of reducing, we have that 1 times the numerator is just 1 minus 2 to the n plus 1, and the denominator is just minus 1. Pushing the minus 1 to the numerator, we simply get that this is equal to 2 to the n plus 1 minus 1. A pretty clean and neat solution compared to what we started with. Now, let's talk about infinite geometric series. They're pretty similar to finite geometric series, although instead of stopping at some n, they go on infinitely. We can express them as the sum from k equals 0 to infinity of a times r to the k. Now, we make the observation that this sum will only converge if the absolute value of r is less than 1. Notice that since the series is infinite, and the power on r gets increasingly large, if the absolute value of r is greater than or equal to 1, the sum will become infinity, and so therefore will not converge. This is important if we wish to find an algebraic expression for s, and we're going to do that now. Let's suppose the absolute value of r is less than 1. Similarly to before, we'll multiply both sides by r, giving us r times s is equal to ar plus ar squared plus ar cubed plus ar to the power of 4, and so on and so forth. Just like before, we're going to subtract these two equations, and we'll notice that all of the terms following a get canceled out, leaving us with s minus r times s on the left-hand side, and leaving us with a on the right-hand side. Doing some factoring, we have s times 1 minus r is equal to a, and rearranging, we're given that s is equal to a all over 1 minus r, given that the absolute value of r is less than 1. Let's try applying our knowledge with some examples. We'll start off with a pretty basic and easy example. We're asked to find the sum of 1 plus 1/2 plus 1/4 plus 1/8. Quickly, we realize that this is a geometric series. Every single term is half its previous. So therefore, we have that r is equal to 1/2, and also we can notice that a is equal to 1. Now, all that's left is to use the formula. Let's call this sum s. We have that s is equal to a over 1 minus r, or in this particular case, 1 over 1 minus 1/2. This is equal to 1 over 1/2, and this is equal to 2. Let's try another one. We're being asked to find what is 3 minus 6 over 5 plus 12 over 25 minus 24 over 125, and plus going on forever. It might be slightly harder to notice, but this in fact is still a geometric series. Notice that the pattern for generating the next term is multiplying the previous term by negative 2 over 5. And because the absolute value of negative 2 over 5 is less than 1, we can use the formula we've previously proved. So if we call this sum s, we have that s is a, or in this case 3, so 3 over 1 minus r, which in this case is minus 2 over 5. Now, this is equal to 3 over 7 over 5, and putting this together, we get 15 over 7, our final answer. Let's go on to the final question. We're being asked to find what is 2 over 5 plus 3 over 5 squared plus 2 over 5 cubed plus 3 over 5 to the power of 4, and going on forever. Now, at first glance, the denominator does follow the pattern of a geometric series. However, the numerator is alternating in between 2 and 3, and so this summation actually isn't a geometric series. However, if we do some grouping, we might be able to find two separate geometric series. Let me show you what I mean. If we group every element of 2, we'll have 2 over 5 plus 2 over 5 cubed, and this will be 2 over 5 to the 5th plus going on, and we also add on 3 over 5 squared plus 3 over 5 to the power of 4 plus 3 over 5 to the power of 6, and going on forever. Now, in the left-hand side, we have that our a is equal to 2 over 5, and every single step we're multiplying by a factor of 1 over 5 squared, or 1 over 25. With the rightmost expression, we have that our a, our first value, is 3 over 5 squared, or 3 over 25, and every next term is just 1 over 25 of the previous. So we have that our sum, s, is the sum of two separate geometric series. In the first one, we have 2 over 5 in the numerator, all over 1 minus 1 over 25, and this is adding on to 3 over 5 squared, or 25, all over 1 minus 1 over 25. Some reducing will yield that this is equal to 2 over 5, all over 24 over 25, plus 3 over 25, all over, once again, 24 over 25. Now, this is equal to 5 over 12 here, and with the rightmost expression, we're given 1 over 8. Now we wish to find a common denominator, which in this case will be 24. So we have 10 over 24 plus 3 over 24, and this gives us our final answer of 13 over 24 is the answer to the sum that we started with.
Alright guys, thank you so much for watching. If you had any questions about the video content or just other video suggestions, drop them down in the comments below. I do try to read as many as possible. And if you made it this far,
oh my god.
And if you made it this far, consider subscribing. It helps me grow my channel and it helps me reach a greater audience and help more people with math. That's all from me. Till next time.